In everyday life, length feels like a simple and permanent property. A table is 2 meters long, whether it sits in your room, travels in a truck, or rests in a warehouse. We instinctively believe that length is an objective feature of the world, fixed, stable, and independent of who observes it. But nature, as revealed by modern physics, is far more subtle and mysterious than our everyday intuition suggests. The idea behind length contraction begins with a simple but profound realization. Measurements depend on the observer's motion. In classical physics, this was not the case. According to the ideas of Isaac Newton, space and time were absolute. A meter was always a meter, and time ticked at the same rate everywhere in the universe. Motion did not affect the size of objects or the flow of time. However, at the beginning of the 20th century, experiments with light and electromagnetism began to challenge this classical view. Scientists discovered that the speed of light always appeared to be the same, no matter how fast the observer was moving. This strange and unexpected fact forced physicists to reconsider the nature of space and time themselves. In 1905, Albert Einstein proposed the theory of special relativity, built on a bold assumption. The speed of light is constant for all observers, regardless of their motion. This single idea reshaped our understanding of reality. But if the speed of light must remain constant, something else has to give way. Space and time can no longer be absolute. Instead, they must adjust themselves depending on how fast an observer is moving. This leads to several surprising effects, and one of them is length contraction. Imagine a long train moving at an extremely high speed, close to the speed of light. To a passenger sitting inside the train, everything feels normal. The seats, the walls, and the length of the train appear unchanged. The passenger could measure the train and find it to be, for example, 100 meters long. This measurement is called the proper length because it is measured in the frame where the object is at rest. Now imagine an observer standing on a platform as the train rushes past at incredible speed. According to classical physics, this observer should also measure the train as 100 meters long. But special relativity predicts something different. Because the train is moving relative to the platform observer, the observer measures the length of the train to be shorter than 100 meters. The faster the train moves, the shorter it appears along the direction of motion. This is not an illusion or a trick of the eye. It is a real physical effect that comes directly from the structure of space and time. The key idea here is that length is not an absolute property. It depends on how the measurement is made and how the observer is moving. When an object is in motion relative to you, the distance between its front and back must be measured at the same instant in your frame of reference. But because time itself behaves differently for moving observers, this measurement produces a shorter length. This is the essence of the statement, motion changes measured length. It is important to understand that nothing physically squeezes the object. The atoms are not being crushed, and the object does not feel compressed in its own frame. From the object's perspective, it remains perfectly normal. The contraction only appears when viewed from a different frame of reference, moving relative to it. In this way, length contraction teaches us a deeper lesson about reality. It tells us that space is not a rigid stage on which events unfold. Instead, space and time are woven together into a flexible fabric that changes depending on motion. At ordinary speeds, cars, planes, even rockets, this effect is far too small to notice. But as speeds approach the speed of light, the contraction becomes dramatic. A spaceship traveling at 90% the speed of light would appear significantly shorter to a stationary observer. Thus, the first key point reveals a profound truth. The size of an object is not a universal constant. It depends on how fast you are moving relative to it. Motion, in the strange and elegant world of relativity, reshapes not only time, but space itself. Only happens at relativistic speeds. In the world of our daily experience, motion seems gentle and harmless. A bicycle moves down the street, a car drives along a highway, an airplane crosses the sky. In all these cases, the objects around us appear unchanged. A moving train does not seem shorter than a stationary one, and a flying airplane does not look compressed along its wings. Our senses tell us that motion does not affect the size of things. For centuries, this everyday observation shaped the foundations of physics. In the framework of Isaac Newton, motion and size were entirely separate concepts. An object could move as fast or as slow as it wished, yet its length remained the same for all observers. The universe in this classical picture was like a vast stage where space and time were fixed, absolute, and unaffected by motion. But nature had a secret hidden in the behavior of light. By the late 19th century, scientists were studying the properties of light with increasing precision. They discovered something deeply puzzling. The speed of light always appeared to be the same, no matter how fast the observer was moving. This strange result defied the logic of classical mechanics. If you run toward a moving object, you normally expect its speed relative to you to increase. But light refused to obey this rule. In 1905, Albert Einstein proposed a revolutionary solution. He suggested that the speed of light is a universal constant, the same for all observers, regardless of their motion. But this simple statement carried enormous consequences. If the speed of light cannot change, then space and time themselves must adjust to preserve this cosmic speed limit. From this idea emerged several remarkable effects: time dilation, length contraction, and the relativity of simultaneity. Yet these effects do not reveal themselves in the slow-moving world of everyday life. They become noticeable only when speeds approach the speed of light. This is what we mean by relativistic speeds. To understand this, consider the equation that describes length contraction. L is equal to L naught multiplied by square root of 1 minus v square over c square. Here, L naught is the proper length of an object, v is its speed, and c is the speed of light. Now imagine an object moving at everyday speeds. Suppose a car travels at 100 kilometers per hour. Compared to the speed of light, about 300,000 kilometers per second, this speed is almost nothing. The ratio, v square over c square, becomes extremely tiny, so the square root in the equation is almost exactly equal to 1. As a result, the length L is nearly identical to the proper length L naught. In practical terms, the contraction is so small that no ordinary instrument could detect it. The difference might be smaller than the width of an atom. For all everyday purposes, the object's length appears unchanged. But now imagine something far more extreme. Suppose a spaceship travels at 90% the speed of light. In this case, the term v square over c square becomes significant. The square root in the equation is no longer close to 1. The observed length becomes noticeably shorter, perhaps only about half its proper length. If the speed increases to 99% of the speed of light, the contraction becomes even more dramatic. The object could appear only a small fraction of its original size along the direction of motion. At speeds incredibly close to light, the contraction becomes extreme, approaching zero length from the perspective of a stationary observer. This is why length contraction is not part of our everyday experience. The speeds required to produce noticeable effects are far beyond those of cars, planes, or even most rockets. Only particles in powerful accelerators, or objects moving through the cosmos at near light speeds, truly experience significant relativistic effects. For example, In particle accelerators, subatomic particles are pushed to speeds very close to the speed of light. At these velocities, length contraction and time dilation are not theoretical curiosities. They are measurable realities. Without accounting for relativity, the behavior of these particles would make no sense. Thus, the second key point teaches us an important lesson. Relativity does not contradict our daily experience. It extends it. Newton's physics works beautifully at ordinary speeds because relativistic effects are too small to notice. But as we approach the cosmic speed limit set by light, the deeper structure of reality begins to reveal itself. In this way, length contraction is not something that happens all the time. It is a hidden feature of the universe, quietly waiting to appear only when motion becomes extreme. It reminds us that the familiar world is just a gentle approximation of a far more profound and dynamic cosmos, one where space and time themselves bend and adjust to preserve the universal rhythm of light. Direction matters. In the quiet world of everyday experience, space appears uniform in all directions. A book on a table has a certain length, width, and height, and these dimensions seem equally real and equally stable. Whether the book is at rest or carried across a room, its shape does not appear to change. To our senses, space behaves like a rigid box in which objects simply move from one place to another without altering their form. But when we begin to approach the strange territory of high speeds, speeds close to that of light, space reveals a more subtle and directional character. One of the most fascinating aspects of length contraction is this. The contraction happens only along the direction of motion. The dimensions perpendicular to that motion remain unchanged. To appreciate this idea, let us imagine a simple object, a long rectangular spaceship traveling through the cosmos. Suppose the ship is moving forward at an enormous speed, nearly the speed of light, relative to an observer watching from a distant planet. Now, according to the principles of special relativity proposed by Albert Einstein, the observer will measure the spaceship's length along its direction of motion and find it shorter than its proper length. The ship appears compressed from nose to tail. However, if the observer measures the width or height of the spaceship, dimensions that are perpendicular to the direction of travel, they will find no change at all. The ship's sides and top remain exactly as they would be if the ship were at rest. This might seem strange at first. Why should only one dimension change while the others remain untouched? The answer lies in the deep connection between space and time. Length contraction is not caused by any physical force squeezing the object. There is no cosmic pressure pushing on the front and back of the spaceship. Instead, the contraction emerges from the way space and time coordinate themselves between different observers. To measure the length of a moving object, an observer must determine the positions of its front and back at the same instant in time. This requirement of simultaneity is crucial. But in special relativity, what counts as the same instant is not universal. Different observers moving relative to one another do not agree on which events happen simultaneously. It is precisely this difference in simultaneity that leads to length contraction. When an observer measures the length of an object moving past them, the measurement involves 2 points in space taken at the same time in the observer's frame. Because time behaves differently for moving observers, the distance between these points becomes shorter along the direction of motion. However, this reasoning applies only along the line of motion. In directions perpendicular to the motion, there is no such interplay between time and distance. The measurements in those directions do not depend on simultaneity in the same way. As a result, those dimensions remain unchanged. You might imagine this effect visually. Picture a sphere traveling at near light speed. To an observer at rest, the sphere would not remain a perfect sphere. Instead, it would appear slightly flattened along the direction of motion, like a ball gently pressed from front to back. Yet from side to side and top to bottom, it would look exactly the same. This directional nature of length contraction has deep implications. It tells us that motion through space is not a simple uniform shift. Instead, motion reshapes the very geometry of objects, but only along the axis in which they move. Interestingly, from the perspective of the object itself, nothing has changed. The astronauts inside the spaceship see their vessel as perfectly normal. Its length, width, and height all appear exactly as they always have. The contraction exists only from the viewpoint of an observer moving relative to the ship. This leads to a beautiful symmetry in relativity. Each observer sees the other's moving objects as contracted along the direction of motion, yet in their own frame, everything appears unchanged. There is no absolute, privileged perspective. The universe does not favor one observer over another. The fact that contraction occurs only in the direction of motion also preserves the consistency of physical laws. If all dimensions contracted equally, objects would simply shrink uniformly, and many physical relationships would be disrupted. By limiting the effect to the direction of motion, the structure of physical laws remains intact across different frames of reference. Thus, the third key point reveals a subtle truth. Space is not affected equally in all directions when motion becomes extreme. Instead, the universe adjusts itself precisely along the path of motion, leaving the perpendicular directions untouched. In this way, length contraction teaches us that space is not a rigid, unchanging grid. It is a dynamic, responsive fabric, one that stretches, compresses, and reshapes itself depending on how objects move within it. And yet, this transformation is not random. It follows a precise and elegant rule. Only the direction of motion feels the effect. Different observers measure different lengths. In the quiet logic of everyday life, we assume that measurements are universal. A ruler is a ruler, a meter is a meter, and the length of an object seems to be an objective fact about the world. If two people measure the same table, we expect them to agree on its size. This belief is deeply rooted in our intuition, shaped by centuries of classical physics and daily experience. In the framework of Isaac Newton, this intuition made perfect sense. Space was considered absolute, like a vast and rigid stage on which the drama of the universe unfolded. Objects could move across this stage, but their lengths remained fixed and independent of who observed them. Two observers, regardless of their motion, would always agree on the size of an object. But the dawn of the 20th century brought a new understanding of nature. With the birth of special relativity, proposed by Albert Einstein, the universe revealed a more subtle truth. Measurements of space and time depend on the observer's state of motion. This idea lies at the heart of the fourth key point. Different observers can measure different lengths for the same object, and both can be correct. To understand this, imagine a long train resting quietly at a station. A passenger inside the train measures its length using a ruler and finds it to be 100 meters long. Since the train is at rest relative to the passenger, this measurement is called the proper length. It is the length of the object in the frame where the object itself is not moving. Now imagine a second observer standing on the platform as the train begins to move past at an extremely high speed, close to the speed of light. This observer decides to measure the length of the moving train. According to classical physics, the observer should also measure it as 100 meters long. But special relativity tells a different story. Because the train is moving relative to the platform observer, the observer measures the distance between the front and back of the train at the same instant in their own frame of reference. Due to the relativistic nature of time, this measurement yields a shorter length. To the platform observer, the train might appear to be only 80 meters long, or even less depending on its speed. Here we encounter something extraordinary. The passenger inside the train insists that the train is 100 meters long. The observer on the platform insists it is only 80 meters long. At first glance, this seems like a contradiction. How can the same object have two different lengths? The answer lies in the relativity of simultaneity. To measure the length of an object, one must determine the positions of its two ends at the same moment in time. But in special relativity, different observers do not agree on what counts as the same moment. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different speed. This means the passenger and the platform observer are not actually measuring the same pair of events. Each measurement is made using their own definition of simultaneity, and therefore each observer obtains a different result. Yet both measurements are perfectly valid within their own frames of reference. In this way, length becomes a relative quantity, much like velocity. Just as two observers moving at different speeds can disagree about how fast an object is traveling, they can also disagree about its length. It is important to emphasize that neither observer is mistaken. There is no true length that exists independently of all observers. Instead, the proper length is simply the measurement made in the object's rest frame, while other observers measure contracted lengths depending on their relative motion. This idea challenges our deepest intuitions about reality. It suggests that space is not a fixed container, but a flexible and observer-dependent structure. Measurements are not absolute truths carved into the universe. They are relationships between the observer and the observed. Yet, despite this apparent strangeness, the laws of physics remain perfectly consistent. Special relativity ensures that all observers, regardless of their motion, will agree on the fundamental laws of nature. The differences in measurement are not contradictions. They are the natural consequences of living in a universe where space and time are interwoven. Thus, the fourth key point reveals a profound lesson. Reality is not built from absolute measurements, but from the relationships between observers. The universe does not offer a single fixed perspective. Instead, it allows each observer to carry their own valid view of space and time, all woven together by the elegant principles of relativity. Given by the Lorentz contraction formula, in the language of physics, every deep idea eventually finds its expression in mathematics. Words may guide our intuition, metaphors may awaken our imagination, but equations are the quiet, precise voices through which nature speaks. They are not merely symbols on paper, they are condensed forms of reality itself, small windows through which we glimpse the hidden structure of the universe. Length contraction, though philosophical in its implications, is described by a simple and elegant equation. This equation is known as the Lorentz contraction formula, named after the Dutch physicist Hendrik Lorentz, whose work laid the mathematical groundwork for what would later become special relativity. It was then given its deeper meaning and physical interpretation by Albert Einstein in 1905. The formula is written as L is equal to L naught multiplied by square root of 1 minus v square over c square. At first glance, it appears to be just another mathematical expression. But hidden inside these symbols is an entire revolution in our understanding of space and motion. Let us meet the characters of this cosmic drama. The symbol L naught represents the proper length. This is the length of an object measured in its own rest frame, the frame where the object is not moving. You may think of this as the object's home length, the size it possesses when it is calm and at rest. The symbol L represents the contracted length. This is the length measured by an observer who sees the object moving at a high speed. It is the length that appears shorter due to the effects of special relativity. The symbol v stands for the velocity of the object relative to the observer. This is the speed at which the object moves through space, as seen from the observer's frame. And finally, there is c, the speed of light in a vacuum. This is not just another number. It is one of the fundamental constants of the universe, approximately 300,000 kilometers per second. In relativity, c plays a central role. It is the ultimate speed limit, the maximum speed at which information or matter can travel. Now look closely at the structure of the equation. Inside the square root, we see the expression 1 minus v square over c square. This term determines how much contraction occurs. Its behavior reveals the heart of the phenomenon. If the velocity, v, is very small compared to the speed of light, the fraction v square over c square becomes extremely tiny. In that case, the expression inside the square root is almost equal to 1. The square root of a number close to 1 is also close to 1. As a result, the contracted length L is nearly the same as the proper length L naught. This is why we do not notice length contraction in everyday life. At ordinary speeds, cars, trains, airplanes, the value of v square over c square is so small that the contraction is practically zero. But as the velocity increases and approaches the speed of light, something remarkable happens. The fraction v square over c square becomes larger and larger. The expression inside the square root shrinks. The square root itself becomes smaller, and therefore the contracted length L becomes shorter. If the velocity gets extremely close to the speed of light, the term inside the square root approaches zero. This means the observed length approaches zero as well. To a stationary observer, an object moving at nearly the speed of light would appear extremely compressed along its direction of motion. Yet there is an important detail hidden in this formula. Notice that the velocity v can never equal c. If v were equal to the speed of light, the expression inside the square root would become zero, and the length would collapse entirely. But special relativity tells us that no object with mass can ever reach the speed of light. It would require infinite energy to do so. Thus, the equation not only describes length contraction, it also preserves the cosmic speed limit. There is a quiet elegance in this formula. It does not shout or exaggerate. It simply states, with mathematical precision, how space itself adjusts to motion. The faster an object moves, the more space compresses along its path. It is as though the universe gently folds space to ensure that the speed of light remains constant for all observers. This equation also reveals the unity of the relativistic effects. The same factor that appears in length contraction also appears in time dilation and other relativistic phenomena. It is a single mathematical thread weaving together the fabric of space and time. In the end, the Lorentz contraction formula is more than a calculation. It is a statement about the nature of reality. It tells us that length is not fixed, that motion reshapes space, and that the speed of light governs the geometry of the universe. What appears as a simple square root is in truth a profound message from the cosmos. Space itself is not absolute. It bends, contracts, and adapts to the rhythm of motion.